Hi, I'm Matthias Eichholz from TU Darmstadt, and in the next 5 minutes I'm going to give you a brief overview of our work on dependently typed data plane programming. If we look at the papers published over the last 25 years at POPL, it seems like quite some people care about dependent types. However, it also seems like the majority of work focuses on the theory of dependent types. But in order to establish dependent types in everyday programming, work is also needed on the practical side. With our work, we show that even the Hello World example of dependent types, lists with statically known length, can serve as a foundation in an important practical domain, namely networks. Reasoning about finite lists of bits is bread and butter when reasoning about network packets. Over the last decade, the way how we can configure networks has changed. With the P4 language, it's now possible to specify the behavior of packet processing devices such as network switches in software. Networks are critical infrastructure underlying almost every modern software system, so runtime errors must be avoided at all costs. Unfortunately, the P4 language is inherently unsafe and does not prevent programmers from writing programs that, for example, unexpectedly drop packets. We therefore want to provide the network programmer with tools to statically check the correctness of programs. And to do so, we built Pi4, a dependent type system that allows programmers to reason at bit level about the correctness of programs. Let's have a look at some of the central features of P4 and how our type system supports them. The central abstraction of the P4 language are so-called header types. They describe the structure of network packet headers, and every possible packet header a program should operate on, so-called header instances, must be declared upfront. The packet pipeline in P4 first transforms an input packet into a type representation, which is called parsing. At runtime, this means that header instances are populated with bits from the input packet. Next, it computes transformations on these headers, and finally serializes headers back to a new packet, which is called deparsing. We take this fact into account in our type system by providing so-called heap types. A heap type describes the system state consisting of both the input and output packet, as well as currently valid instances, which can be safely accessed. P4 provides state machine-based abstractions to describe the parser, while the transformation stage and the deparser basically consist of a sequence of imperative commands paired with some control flow. Pi4 provides a more uniform syntax. It's basically an imperative language with a few domain-specific commands. We assign a dependent function type to every command, where the input type describes the program state before the execution of the command, and the output type describes the program state after the execution. Using a dependent function type, where the output type can reference the input, allows us to relate both program states. The biggest overall challenge is to retain precision while type checking. For every command, we want to capture the effect it has on the current program state. The first thing we need are refinement types, which allow us to make assertions about heap types. For example, that some header field contains some specific value. We also want to precisely track the outcome of conditionals, which we achieve by combining union types with refinement types. And finally, we want to capture the effect of parsing headers from the input type, which we achieve by providing a refinement transformer called chomp. Given some input type, chomp computes a new type that captures the effect of removing a fixed number of bits from the input packet and populating a header instance with these bits. We proved that all type system features we combined are actually sound and that the resulting type system is decidable. We implemented the type checker in OCaml, and in our implementation we encode subtyping checks into an SMT problem, which means that for programmers it's not necessary to do any manual proofs. Our type system is capable of expressing a wide range of interesting properties. We can express invariants on network protocols, for example check that the implementations follow specifications. We can check that certain headers are not valid at the same time. For example, a network packet will never be an IPv4 and an IPv6 packet at the same time. And finally, we are able to verify program properties in a modular way, which enables an open world model in which third-party components can be plugged into existing programs without violating application-specific constraints. To learn more about Pi4, our dependently typed data plane programming language, I invite you to see my full talk at POPL 22.